Welcome to this lecture in the ongoing series of lectures in real analysis. Today we'll be looking at the analytical definition of differentiability, which is the traditional definition as found in textbooks. Let us look at what we did the last time. Last time we defined what is meant by right differentiability at a given point and left differentiability and differentiability. So let's first talk about this. So we said that a function is right differentiable at a point if the right tangent at the corresponding point in the graph exists. All right. And then suppose now we have a function with a point a in the domain and I is an interval. Then we define the notion of differentiability of f at a, making three separate cases. The first was when a is in the interior of I. In that case, we said that f is differentiable at a if it is both left and right differentiable at a, and the slopes and the slopes of the left and right tangents are equal. So that is the notion of differentiability at an interior point. If a is the left boundary point, then we say that f is differentiable at a if it is right differentiable at a. It doesn't make any sense to ask for left differentiability at the left boundary point of the interval. Similarly, if a is the right boundary point, then we say that f is differentiable at a if f is left differentiable at a. Okay. Now finally we define derivative. So the right derivative of f at a is defined as the slope of the right tangent at the point a comma f a on the graph of f, and we denote the right derivative by this symbol f subscript r. This is a prime and then bracket a. All right, and then lastly we discussed the fact that if a function is right differentiable at a point, then it is also right continuous at that point. I made a slight mistake in the argument that I gave. So let me repeat quickly what the argument was. So again, the hypothesis is we have a function defined on an interval, and a is a point which is not the right boundary point, so that we can talk about right differentiability at that point. So our conclusion is that if f is right differentiable at a, then f is right continuous at a. This is what we want to prove, and what we did was we fixed this, we located this point a comma f of a. This is a point in the graph of the function, and we chose an epsilon greater than 0. We made this right epsilon band, which is which we denote by b subscript epsilon and a comma f of a, just an ad hoc notation for the purpose of this particular proof. And now what do we want to show? We want to show that there exists delta greater than 0 such that the graph of the function above a comma a plus delta is contained in this right epsilon band, exactly as the last time. This is what we want to show. And here is where I made the mistake. I said that there exists, so rather note that there exists beta greater than 0 such that what happens? Such that if you take the point a plus beta, right? Last time I just said beta, that was a slip of tongue. So if you take the point a plus, take the line corresponding to the x coordinate a plus beta, meaning all the points whose x coordinate are equal to a plus beta, that line, and just consider the left half plane corresponding to it, then the points in the cone which are in that left half plane, and the points in this cone and in the left half plane, all of those will be completely contained in this right epsilon band. So let me write it and then again explain. So note that there is beta greater than 0 such that the left half plane corresponding to a plus beta intersection c epsilon c alpha rho, So alpha is just any positive real number, and we have just made that alpha cone. Alpha has nothing really to do with epsilon. So this is contained in b epsilon a comma f of a. And this is something that one can easily prove. So there is beta greater than 0 such that if you take this line, which is x equals a plus beta, and just consider all the points which are on the left of this line and simultaneously are in this cone. So the intersection is basically just this. The intersection is just that much. And this is contained in the right epsilon band. So the claim is that there is one such beta. The mistake that I made last time was instead of a plus beta here, I just wrote beta, which doesn't make any sense. So that was just a slip of tongue, basically. So there is such a beta, and now by the fact that rho is the right tangent, at a comma f of a, etc., there is delta greater than 0, which we can assume is at most beta. Everything else that I said is exactly the same except for that little adjustment of a plus beta rather than beta. So we can there is delta greater than 0, which we can assume is less than beta, such that the graph of the function above a comma a plus delta is contained in the alpha cone. But this is already contained in the this part, because delta is at most beta. So this is already contained in this part, and therefore what this implies is that gamma f restricted to a comma a plus delta is contained in C alpha beta intersection H alpha plus beta minus, which is contained in B epsilon a comma f of a. Right, so this is what we wanted to show, and we have shown it. There is a delta greater than 0 such that this happens. So yeah, so basically this was the only mistake. Not really a mistake. I'm sure you were able to fix it for yourself. Anyway, so these are there is only one very simple problem. And now let us get to the material of this lecture. So as I said, this I write definition in the heading, but it is not a definition. We have already defined what is meant by derivative. So we'll be proving a theorem which will show an equivalence between an analytical characterization and the geometric definition that we gave. Again, so what we have is an interval and a point which is not the right boundary point, meaning there is a right neighborhood of a contained in I. Okay, and now let f be a function from the interval to R. Then the following are equivalent. What are equivalent? The first is that f is right differentiable at A. The second is this limit exists. And the third is there is a function such that A is a right continuous at little a, and f of x minus f of a equals ax times x minus a for all x and I. Alright, let us prove all of these things. Okay. So before we get into the proof, let me just recall one thing which I gave as an exercise last time. Is that recall that the epsilon cone about array rho is, well, what is rho then? I have to say what is rho. So let's say, okay, so this is in brackets. So if rho is equal to x comma m x minus x naught plus y naught x greater than equal to x naught, if this is a right ray starting at a point x naught comma y naught in the plane, then c epsilon rho is given by c epsilon rho equals, you put this point in it, and then the rest is all those points in R2 where x is greater than equal to x naught, and well, x is strictly greater than x naught, and y minus y naught x minus x naught, this is not away from m by more than epsilon. So this was a very simple exercise that I gave the last time as problem, and we'll use it. And there's not much in here, but anyway, I have to state it just for the peace of my mind. Okay, so now we'll show one implies 2. So one says that the f is right differentiable at a, so let rho equals x comma m x minus a plus fa be the right tangent at a comma fa to the graph of f, and we will show that this limit is equal to m. Not just that it exists, but it is actually equal to the slope of the right tangent. Okay, so how do we do it? Now by 1, there exists delta greater than 0. So okay, so fix an epsilon greater than 0. We want to establish a limit, so let first fix an epsilon greater than 0, and now by 1 there is delta greater than 0 such that the graph of the function restricted to a comma a plus delta is contained in the epsilon cone about the right ray, which is same as saying that when you take x in, well, in particular this implies that when you take x in a comma a plus delta in this open interval, I could have written a closed interval here, but I just care about this particular implication. So therefore, whenever you choose x in this open interval, we have x comma fx in this epsilon cone, just rewriting the above thing, except we forget about this point. Okay, which means that if you have a less than x is less than a plus delta, then now we use this yellow thing, we use that thing to write m minus epsilon less than fx minus f of a, x minus a is less than, Or why should I write this? I'll just directly write f of x minus f of a, x minus a minus m in the absolute value is dominated by epsilon. Okay, and this shows that the right limit exists because you have a right deleted neighborhood of x in which this inequality is satisfied, which means that therefore this limit exists and is equal to this is equal to m. That's it. Very simple. 2 implies 3. So we'll just construct this function a that we need to construct. This one, we'll just construct it, and there's an obvious choice for it. So define b from going from this to r as bx equals this ratio This makes sense because this guy is not vanishing at any point here, so it makes sense. And now now we will define a. So define a from this to that as ax equals bx if x is not equal to a and is equal to this limit. If x equals a. So by 2, we are assuming 2 is true, so this limit exists. And therefore, this is a well-defined thing. And we claim that a is right continuous. So to see that a is right continuous, we check that limit of x going to a plus ax equals a of a. This is what we need to check for right continuity. So how do we do that? So we have limit x going to a plus ax. We just use the definitions, and this is equal to limit x going to a plus bx. Why is that? This is because ax is equal to bx when you are not equal to a, and since we are taking limit, we don't care what is the value of a on little a. So therefore, this limit is equal to that limit. The behavior of ax and bx are precisely the same away from the point little a. So these two limits are equal, but what is bx? Bx is this f of x minus f of a, x minus a, but this by definition is the value that a takes on little a. So this is a of little a, and that's it. So we have checked for right continuity. This is what we needed to check, and we have checked it. So a is right continuous. And lastly, lastly, it is clear that f of x minus f of a equals ax x minus a. Why is that? Because if you substitute x equals a, then both sides become 0, so there is no problem. And if x is not equal to a, then ax is just bx, and the way bx is defined, you'll see that these two things are equal. So clearly holds for x not equals a. And that's it. So this means 2 implies 3. Now we go the other way. So we'll show 3 implies 2. Okay, so this time we will assume 3, meaning this thing is true. Okay, fine. So let a be a function which is right continuous at a. such that fx minus f of a is equal to ax x minus a for all. Okay, but then this limit is clearly equal to this limit, which exists because ax is right continuous at a. So this shows that, and this shows 2. So 3 implies 2. And now 2 implies 1, which will finish the proof. So for 2 implies 1, let m equals this limit, which exists by hypothesis. All right. So we'll show that the right tangent to the point a comma f a exists and has slope m. So let rho be the ray with slope m starting at a comma f a. So what we want to show that if we take epsilon greater than 0, then there is a delta greater than 0 such that the graph above a comma a plus delta is contained in the epsilon cone about this right ray. But by 1, by, okay, no, let's not say 1, let's say by star, we have delta greater than 0 such that whenever x is in a comma a plus delta, we have f of x minus f of a on x minus a minus m is at most epsilon. And this implies that if you choose x in a comma a plus delta, then x comma fx is in the epsilon cone about the ray. And again, we are using this yellow thing, which is a trivial fact again, and which implies that the graph of f above a comma a plus delta is contained in this guy, because it is, if I put a round bracket here, then this happens because of that, and f of a comma f of a is clearly contained in the epsilon cone, just that's immediately by the definition of the epsilon cone. So this happens for free, and therefore we are done. That finishes this proof. Okay. So this, the geometric definition is nice for understanding, but if you want to really calculate the derivative, meaning the slope of the right tangent, this is the most useful thing. So let's take an example, very simple example. So we have, let f. Yeah. So before I go there, before I go to an example, I proved a theorem for right derivatives, etc. Right tangent, but you can prove a similar thing for left tangent, and you can also prove the similar thing for functions which are differentiable. So if f is differentiable at a, then you can show that this, you can forget about this plus, then this will exist, and this right, you can forget about this right, and so you can easily formulate the corresponding variants, which I will not do. I assume that you will do it for yourself and use those theorems without warning. So now let us go into the example. So let f be defined as our favorite function. So then we compute let's compute this guy. We don't even know a priori if it exists, but in the computation, the course of the computation will show that it does exist. So we are worrying about this thing, which is x square minus limit x going to 1 plus x square minus 1 x minus 1, which is limit x going to 1 plus x minus 1 x plus 1 upon x minus 1. And now I can cancel these two things because we are only worried about the places where x is strictly greater than 1. We are taking the right limit. We don't care what happens at x equals 1. So the above limit is nothing but this limit x plus 1. But now we can do the algebra of limits to write this plus 1, which is 1 plus 1, which is 2. So the right limit exists and is equal to 2, and you can easily show that the left limit exists and is also equal to 2. So what I'm saying is that this is also equal to 2, and the function in fact is therefore differentiable because the slopes are equal. So one can summarize the above discussion by saying that f prime, the derivative of f at 1 equals 2. I don't think I introduced this notation. So if the function is differentiable at a point, then its derivative is denoted by f prime at that point. So this is the case. And in fact, you can show that the derivative exists not just at 1, but at every point of the real line. This is a particularly nice function. It is differentiable everywhere. And you can calculate the derivative. That's an exercise. In fact, you must have done this in high school, albeit non-rigorously. Sorry, what did I do? Right. So this is all. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.